Okay, so we will be recording this session. If anybody has any objections with the recording, please say so now. Okay, so we've already seen, we already talked about resistors in series. So when we have resistors in series or a series array, the current is going to be the same through all of the resistors. Their voltage is going to be divided or distributed. And the equivalent resistance, which is a resistance that it's one resistance that has the same effect or combined effect as each of the individual resistances together. That's the equivalent resistance. In the case of series, we just added, it was the sum of the resistances. Now, with regards to resistors in parallel, we are going to see that in parallel, there is going to be one current that is going to be divided. So in parallel, the current is divided. 1, 2, 3, and 4. These are being divided, and the voltage, the voltage is going to be the same. Okay, so we're going to have a total voltage here in the circuit. We're going to have a total voltage here, and that voltage is going to be the same in each of the elements. So we're going to have a voltage V here, a voltage V here, a voltage V here, and a voltage V here, and the voltages are going to be the same in parallel. Now, the equivalent resistance is going to follow the reciprocal, the sum of the reciprocals rule. So the equivalent resistance, or the reciprocal of the equivalent resistance, is going to be the sum of the reciprocals of each of the resistances. So 1 divided by the total resistance is going to be equal to 1 divided by R1 plus 1 divided by R2 by R3, as many parallel resistances we have. Okay. Something important here is that in the case of a series connection, the total resistance is going to be larger, or the equivalent resistance is obviously going to be larger than each of the individual resistances because we're adding them up. In the case of the equivalent resistance for parallels, the equivalent resistance is going to be smaller because of the mathematical representation. The potential drop or voltage is going to be the same in each resistors, and the total current is divided. So remember that in series, the voltage is divided, current is the same. In parallel, current is divided, voltage is the same. In series, equivalent resistance is the sum of each of the individual resistances. In parallel, the equivalent resistance is going to be the reciprocal of the sum of the reciprocals. Okay. Okay. And let's do an exercise here. So now we've got this example. We've got 3 resistors that have a value of 1 ohm, 2 ohms, and 3 ohms. These are connected in parallel, and the parallel array is connected to a 3-volt battery. We're assuming that the battery has negligible internal resistance. Remember that this is important because the battery is an EMF, and all elements have internal resistance, and we need to know if we're going to have to consider that or not. In this case, we're not. We have to do the same things we did for the other one. Draw the circuit, find the equivalent resistance, find the current supplied by the source to the parallel circuit, the currents to each resistor, and the power that's dissipated by each resistor. Okay. I'm going to give you a few minutes to try to do this on your own. And we're going to come back and do it here together. Okay. So going to give you a few minutes. Try to do this on your own, and you may ask questions if you wish. Okay, so let's give it a shot. Let's see how we can approach this. So we've got 3 resistors, 1, 2, and 3 ohms, and we've got a 3-volt battery. The 3 resistors are connected in parallel. The first thing we're going to do is draw the circuit. So um, it's important for us to remember. I just want to check what colors did I use for the other circuit. Red. Oh, we used red because I think that, Lucia did that drawing and she started using red. So I'm going to use red also here. So first off, we've got 3 resistors that are connected in parallel. So the thing with the parallel connections, remember, is that the component, the resistor, has 2 terminals. So the 2 terminals have to be connected together. So what we have is that we've got 1 resistor. I'm going to call this R1.
Professor,
Yes.
can you go back like 2 seconds? I just want to take a picture to the problems, please. Because
Sure.
I'm writing in there.
Sure.
Okay.
Let me clear the drawings. What I'm going to, let's do this because we are here to provide support. We want to
Thank
make
you.
things easier, not more complicated. So what I'm going to do is that I am going to send you guys in the chat this screenshot. So so everybody has it, okay? I work for you, not the other way around. Let's see. Desktop in a moment. Okay, here's the screenshot. Okay, so there you got the screenshot of the problem, just so you have it there. Okay, so we've got 3 resistors that are in parallel. So let's do the drawing of the circuit first. And so we've got 1 resistor here, R1. I'm going to draw another resistor here. R2. And I'm going to draw the other one here, R3. Okay, R1, R2, and R3. Sorry about the background barking, but again, as I mentioned, I've got 2 schnauzers and a 5-year-old daughter, and whenever anybody rings the bell, the 3 of them become chaotic. So I've got the 3 resistors here. Now we've got the power supply, also the power source, the EMF. Now the important thing here is that this is a parallel connection because each of the terminals are connected. Let's say that this terminal up here, I'm going to call this terminal A for each of them. All of the terminal A's are connected together, and the terminal B is also connected together. So that makes it a parallel connection. Now we've also got a power source. The power source, or the EMF, is also connected in parallel to the circuit. So what we're going to do is we're going to bring this over here. Okay. And we're going to connect here the power source. I'm going to put a reference here, positive and negative. And this is going to be a 3 volt. Well, we're going to call this, I'm going to call this VS, which is the voltage of the source. And just as a reference, we know that R1 is 1 ohm. R2 is 2 ohms. And R3 is 3 ohms. And the power source, or the EMF in this case, is going to be 3 volts. This is the information we have. Now, the first thing we want to find the equivalent resistance. So in the end, we want to turn this circuit into an equivalent circuit for the purpose of the analysis, where we've got our power supply. And we have one resistance, which is our equivalent resistance. That is going to be the resistance that has the same effect as these three resistances. How do we find that equivalent resistance? We find that equivalent resistance by doing remembering that for a parallel array, the equivalent resistance is going to be the reciprocal of the sum of the reciprocals. So the equivalent resistance is going to be 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. And the reciprocal of that. Okay, that's how we find that's how we find the equivalent resistance. Okay, still isn't 100%. And so we've got three values of resistance there. So we're going to have 1 divided by 1 ohm plus 1 divided by 2 ohms plus 1 divided by 3 ohms, the reciprocal of that. Can you please help me out with the calculations and give me the value of the equivalent resistance? It'd be really helpful. 1 divided by 1 plus 1 divided by 2 plus 1 divided by 3, and the inverse or the reciprocal of that, please.
Professor,
Yes, JC.
I think that the problem said that it was 2 ohms on number 3. It was 1 ohm and 2 ohms, 2 ohms.
Oh, you guys.
Yes, I think it's ohms.
Okay.
The third resistor.
Okay. Remember that we're being recording this, so try not to. Oh, the R3 is 2 ohms. Try not to make me look completely like a doofus. So please make those comments before we're so advanced in the problem. But it's not a problem. We'll just correct this here. It's not going to be a problem. We're just going to do this. By the way, yesterday one of the students from the 4th semester global programs, he sent me a video because we had the electronics class last semester. There are these videos you can find on YouTube that it's this guy. I think he's Indian or Pakistani, but he does these sort of tutorial videos in YouTube. I'm going to share it. I'm going to share it in the WhatsApp. And it's so funny because he always gets electrocuted. So he's explaining a lab exercise or whatever, and he always gets electrocuted, things blow up, but he keeps doing the videos. I don't know if he's a professor or not. Yeah, I don't want to end up looking as doofusy in these videos as that guy. So please, thank you for noting the mistake. Just everybody, let's try to do that a little bit before. The good thing is that we hadn't done any calculations moving forward. I'm sharing the video in the chat. So we've got 1 ohm, 2 ohm, and 2 ohms, right? And so that means that this one is 2 ohms. Okay. Okay, this is going to be 2 ohms. So it's going to be 1 plus 0.5 plus 0.5. It's going to be 2. 1 divided by 2. This is 0.5, right?
Yes.
Yes.
0.5 ohms. And notice what we had talked about, 0.5 ohms. 0.5 ohms is smaller than any of the individual resistances. This is important for the array. So we've got three resistances that have certain values. When we generate a parallel array, the equivalent resistance is going to be smaller. And why is this important? Because again, the parallel array helps me divide current. So imagine that I have a power source, again, that's generating a certain energy. And I've got three things that need to receive part of the current of that energy, but they need to receive it differently. So the parallel array is going to divide the total current into different proportions, and so we see that here. Now let's talk about, so just as a reference, this is A, this is B, okay. And now we're being asked for C, we're being asked to find the total current that the circuit has. So, well, first off, before we move on, questions with this calculation we did here, or what we did in A or B. Okay, so now our circuit, our power supply is providing a current. This I'm going to call current I. And because it's a parallel array, that current is being divided into proportionally into three parts, I1, I2, and I3. So imagine that we've got, again, a pump, and that pump is providing water, fluid, and then we've got three pipes. And so the fluid is going to be divided into the three pipes, okay? And depending on the constriction of each of the pipes, is going to be the pressure that each pipe, that it's going to be, I'm sorry, the amount of current that's going to go through, or the amount of fluid that's going to go through for the same amount of pressure, okay? And so we want to find this value of I, this total current that's being provided. And so we're going to have this total current here. And so we can find the equivalent resistance, and since we have the voltage, we can use Ohm's law to find the total current. The total current is going to be equal to the voltage in the power supply divided by the equivalent resistance. Okay. Now, the total voltage in the power supply is 3 volts, and the equivalent resistance is 0.5. 0.5, oops, 0.5 ohms. And so the total current in the circuit is going to be 6 amps, right? Is that calculation correct? Let me know you people are alive.
Yes,
3 volts
6.
divided by 0.5,
Yes.
it's going to be 6 amps, okay? So that's the total current that's being provided. And that total current, so this is what we're being asked for in C. That total current somehow is going to be divided proportionally into each of the resistors. Okay. I'll do a quick screen save here. Okay, and a couple of questions in the chat. Give me a moment. Okay. So questions up to this point before we go to the next part, which is that division of current that we're talking about. No? Okay. So now we want to find that current, that division of current that's going to be proportional. So how do we do that? Well, the current I1 or the current in R1 is going to be equal to the total voltage. Well, let me write this down here on the, I'm going to do it like this. I'm going to clear this on the bottom. Okay. Remember, all of this is going to be recorded and it's going to be in the slides. Okay. Just remember, let's just remember the values. Okay. So I'm just going to write this down here. The equivalent resistance, we had already calculated it, which was 0.5 ohms. And the total current I, we had already found that is equal to 6 amps. Just to have that as a reference, okay? And so for each of the currents that are going to be divided, okay, and also remember that for the purpose of the exercise, this is B, and this is C, okay? The total current is going to be divided. Now, the current 1 is going to be equal to the voltage in resistor 1 divided by resistor 1. The current in resistor 2 is going to be equal to the voltage in resistor 2 divided by resistor 2. This is just applying Ohm's law. And the current in resistor 3 is going to be equal to the voltage in resistor 3 divided by resistor 3. However, we know that these 3 voltages are the same. Okay, we know that voltage 1 is equal to voltage 2 is equal to voltage 3 because it's a parallel array, and all of these voltages are equal to the voltage of the source. Okay. So because it's in parallel, the voltages are going to be the same. So this is equivalent to having Vs divided by R1, which in this case would be 3 volts divided by R1 is 1 ohm. And so that would mean that the current for resistor 1 is going to be equal to 3 amps. Okay. Remember, if you have any questions, please stop me at 1. Now we've got V2 divided by R2. Since the voltages are the same, this is going to be the same as having Vs divided by R2. And so this is going to be the same as having 3 volts divided by 2 ohms. And that means that I2 is going to be equal to 1.5 amps. And I3 is going to be the same because it's also 2 ohms. So I3 is going to be equal to V3 is the same voltage in the source divided by R3, which is going to be 3 volts divided by 2 ohms. This means that I3 is going to be equal to 1.5 amps. Okay. And so notice here that if I add these, it's going to be equal, or it has to be equal to the total current. Okay. Because again, we're not creating or destroying energy, we're just transferring it. So I've got a total current that's the 6 amps, and that those 6 amps are going to be divided proportionally into the 3 resistors. Okay. This is basically what they're asking us to do in D. Okay. Okay, questions with this one before we go to the last part?
No questions, Professor.
Okay, good, thank you. Okay, so I'm going to take a screenshot of this. And I'm going to erase the lower part. Okay. I'm going to erase this part here. The last thing that they're asking us for is to find the power that's being provided by the power source and the power that's being absorbed or consumed by each of the resistors. Okay, so I'm just going to write this down here just so we have it as a reference and not forget these values. We know that BS is 3 volts. We know that I1 is equal to, we said it was 3 amps. I2 is I1 is 3 amps. I2 is 1.5 amps. And I3 is 1.5 amps. And so what we've got here now is that we have a power here from the power supply, a total power that's being provided. We've got a power from resistor 1, a power from resistor 2, and a power from resistor 3. That's the power that's being provided. The power for the power source is going to be equal to the voltage source multiplied by the total current. And so this is going to be equal to 3 volts multiplied by 6 amps. And so the total power for the power source is going to be equal to, let's say 3 times 6, it's going to be 18 What are the units for power?
Watts.
Watts, perfect. 18 watts, perfect. Let's finish up this part and then we'll take the break, okay? So I don't have to cut the videos too much. The power for resistor 1. Okay, I don't know if you heard that or not. If you did, it was recorded. It was recorded, and so I'm not going to get into that. I'll explain out of the recording what's happening. Power 1 is going to be voltage 1 multiplied voltage 1, which we know is the total voltage, multiplied by current 1. And we know that voltage 1 is the voltage of the power source, which is Vs multiplied by current 1. This is going to be equal to 3 volts multiplied by current 1 is 3 amps. So that means that the power for resistor 1 is going to be 9 amps. 9 watts, I'm sorry. By the way, we're going to do the calculations, but do we need to know? Can somebody tell me what is the power in resistor 2 and 3 without having to do the calculations by default because of what we've been talking about?
The half of the power one.
Yes, that's a good observation. Why? Because we're looking at the proportion. We're looking at the proportion, and the proportion, one resistor is 1 ohm, the other are 2 ohms. There's a proportionality there, and the currents are half. And so what would be that value? I think it was Carmina who spoke, or Karen, who
9/2, 4.5.
4.5, without having to do the calculations. Without having to do the calculations, we know that, and I'm going to do them anyway, but this would be 4.5 watts. And this would be 4.5 watts. And we know that the sum of these has to be equal to the sum of these, oops, has to be equal to the total watts. But if we do the calculation anyway, power 2 is going to be equal to voltage 2 times current 2, which is the voltage of the source multiplied by current 2. Power 3 is actually going to be the same. It's going to be voltage 3 multiplied by current 3. This is going to be equal to voltage of the source multiplied by current 3. And so here we're going to have exactly the same calculation because of the values. This is going to be 3 volts. 3 volts. Multiplied in this case by 1.5. And this is going to give us the 4.5 volts that we're talking about. Okay, and so the total power, the difference between, remember, the difference between the power supply or the EMF and the resistors is that the power supply is providing the power, and the resistors are absorbing that power. That's why the power supply is giving 18 watts, and those 18 watts are being distributed proportionally into the 3 resistors into 9 watts, 4.5, and 4.5. Okay. Okay. Questions with this one before we take a break? Okay, we'll take okay, we'll take a 10-minute break, and we'll come back. Okay, so now that we've talked about resistors in series or series arrays, and we've talked about parallel resistors, now let's talk about combinations of these. Because in the end, in a circuit, we're going to have both series and parallel connections. We're not just going to have series and not just going to have parallel connections. We're going to have a combination of these. And when we have an array of resistors that have different combinations in series and in parallel amongst them, in the end, we want the same thing. We want to find it, we want to be able to do an analysis of the circuit, and we want to be able to know what the equivalent resistance would be for that circuit, considering the individual effects of each of the resistances according to how they're connected, and how that could be reflected with one resistor that has the same effect. So we already talked about equivalent resistance. So if we've got 3 resistors connected in series, we can have an equivalent resistance here. If we've got 2 resistors in parallel, we can have an equivalent resistance over here. Now let's see what happens when we've got a combination of these resistors in series and in parallel. And these problems are very similar to the capacitance problems that we did. We have to kind of identify the connections and start reducing the circuit until we get to just one resistance value, and then we start to unravel the circuit backwards to find each of the individual voltages and currents. So it's kind of like, I wouldn't say these are like puzzles. It's more like or rather they're like these puzzles where you unravel things. I don't know if you've seen these puzzles, or I don't know if any of you have any sort of necklace that's made of fine chainmail or connected chains, links. And when those get bunched up in each other and generate a knot, and you kind of have to unravel that, that's kind of the way I interpret these circuit situations. So now let's look at some examples of resistors in series and in parallel. Okay, and so now we've got this circuit here. Now we are, from now on, mostly in most of these exercises, we're going to be given a circuit. Okay, these are going to be resistive circuits, so we're only going to have resistances and power sources. Notice here that this is another way of representing a power source. This symbol here, which is basically, if I do a zoom, it's kind of like this. This is another way of representing a power source. Another way of representing a power source is the way we've done it, which is like this, for example. We're always going to have a reference, or we're going to have to try to have a reference of positive and negative, at least in DC circuits. Another way of representing a power source is like this, just with 2 bars, that the bars are of different sizes. Notice that one bar is larger than the other. It's not like a capacitor where the 2 are the same. So these are different ways of representing power sources or EMFs. Okay, remember that these are all of these are EMFs, or electromotive forces generators. Okay, they're the power supplies. Okay. And so now we're given this circuit. How many resistors do we have in this circuit? Can somebody tell me?
4.
4 resistors, and we've got 1 power supply. These first exercises, by the way, we're just going to have 1 power supply. We're going to do some other exercises or examples of circuits where we've got more power supplies and different types of power supplies, voltage and current. And we're going to have to use, that's the next topic, which is Kirchhoff's laws. And we're going to see those. But right now, we're just got 1 power supply and 1 circuit. And so what we need to do is we need to turn this circuit, first off, we need to turn this circuit into 1 circuit with one resistance that's equivalent to the array. And the same voltage. By the way, for these circuits, I'm not going to get picky when you do the circuits in the drawing. I'm not going to get picky on the drawing of the power supply, of the symbol. Okay, I'm just using the same symbol they're using here, but you can use the circle with the plus negative. I'm not going to get picky on that. Don't worry very much. However, it doesn't really matter for this circuit, but in other circuits that we're going to see, the polarity is important for a power supply. So it's not the same for the power supply to be positive, negative, than negative, positive. So the polarity is going to be important to mark it in the circuit, but the symbol we use, don't really worry that much about that. So we want to get from here to here, okay? Can somebody, looking at the circuit, can somebody identify how we could start off the reduction of the circuit? How could we start making the resistors, combining them to make them into one resistance? Is something that you see there that we could
With
start off with?
we can start off with 1 and 3, and then you have like the whole, like now you're going to have the combination of 1 and 3, and then 2 and 4.
Okay, let's see that, Lucia. And this is important when we're analyzing the circuit. You're speaking about resistors 1 and 3, right? Those are
Yes.
the ones you're mentioning? Okay.
Yes.
Now, I'm gonna, remember, there's no wrong answers. We're learning here, okay? So don't worry about the answers. We need to clearly identify, we're gonna be, one thing that's correct in what you were saying, Lucia, is that we're first gonna try to identify pairs of resistors that we're gonna try to reduce in pairs. But when we do that, Lucia, the rest of the group, we wanna clearly identify if they're connected in series or parallel. Okay. Now, R1 and R3, how are they connected? Are they connected in series, in parallel, or neither?
Series.
Could you say that again, Jesse?
Series.
Neither.
Actually, neither. They're not connected in series, and let me just draw this. Let's see why. For them to be connected in series, they would need to look like this. What is the difference between this and this? Can somebody tell me?
Like there's another line, or I don't know how to say it.
There's another connection, correct, Carmina? There's a connection here in the middle. Okay. For something to be in series, remember that it's the chain. So it's, let's say that R1 is Lucia. You've got two arms, Lucia. One of your arms is connected to something. Your other arm is connected to one of JC's arms, and the other arm of JC is connected to something else. But in the middle, where you two guys are joining, there's nothing else. Okay? Do you guys see that?
Yes.
Yes.
This connection here, there's something else in between. Okay? That means this is not a series connection.
Professor.
Yes, go ahead, Carmina.
So could it be first R1 and 2 in series and 3 and 4 in series?
Okay, let's analyze that. So first, before we go with what Carmina was saying, is it clear that R1 and R3 are not connected in series?
Yes.
Is it clear that they're not connected in parallel either? Because a parallel connection, both terminals of the resistance have to be connected to the corresponding terminal of the other resistance. So the parallel connection is when we're joining arms like this. So that isn't occurring either. So this is neither a series nor a parallel connection. So is that part clear? And then we're going to go with what Carmina was saying. Okay. Now let's look at what Carmina was saying. So Carmina, you were saying we're going to grab 1 and 2.
Yeah, but I see now that they're connected with the two arms, right?
Yes. So
So it's
if we,
parallel.
yeah. So well, no, actually, first let's look at this. Are they connected in series? No, because we've got something else here. You see that? So they're not in series because we've got a separation here. For them to be connected in series, there should be nothing here. And the
Professor, I have a
other,
question.
yes, go ahead, please. Lucia.
Okay, no, continue. Right now, I'll tell you the other one I was going to say.
Okay, let me just finish this, and there's another one that's clearly what we're looking for. So, Carmina, first off, they're not in series. Is that part clear?
Yes.
Yeah, sorry, yes.
Now, well, we could say, well, they're in parallel. Well, no, because for them to be in parallel, here they're joined in one terminal, but over here, the other terminal is connected to something else. For them to be in parallel, these two terminals would have to be connected together, and they're not. So this isn't a series or parallel connection either. We can't start off there. Is there any other? I think Lucia, you wanted you were
I was going to
thinking
ask if we can do F3 instead of pairs.
Yes, but it's the same principle. The three of them have to be connected completely in series or completely in parallel. Okay. So I would recommend going in pairs. Okay.
So it could be 3 and 4 because
correct.
there's nothing. Okay.
Correct, Lucia. Let's look at 3 and 4. Are they connected in series? Yes, because there's a little chain going on here. So again, this is one arm of Lucia, the other arm of Lucia, one arm of JC, the other arm of JC. They're holding their hands, and there's nothing here in the middle. There's nothing separating them, okay? So they're in series, okay? By the way, something can't be in series and in parallel at the same time. So it's either in series, in parallel, or neither, okay? So this combination here is something we could start off with, okay? And if they're in series, then what would be the resulting resistance of these two if they're in series?
10.
10 ohms, correct. Do you see how we could start off then? Are we okay up to this point? Again, these problems are going to be kind of like unraveling things, okay? Oops. Okay, okay, so let's start unraveling and see this. Well, first off, we are going to grab these two, like Lucia mentioned, and we're going to calculate an equivalent resistance, which we just found is 10 ohms. Okay. By the way, a recommendation, please do this in the exam when we get to that point or in exercises. Try to be as ordered as possible in your steps. Okay. So I can clearly understand your logic, and use some sort of nomenclature to identify what you're doing. So the combination of 3 and 4, I'm going to call R3 plus 4, and it's going to be 10 ohms. That's the first step of the reduction. Now, what could be the next step here? We've gone from here
Parallel.
to here. Okay, Carmina, which ones you have identified a parallel connection? Which would be clearly in parallel?
2 and the one that is 3 plus 4.
Correct, Carmina, very well, very well done. So now we've got these two. Use different colors, just so eventually going to end up. I'm going to end up with less colors. Now I'm going to grab these two. These two are clearly in parallel. Why? Because this terminal is connected to this terminal and this terminal is connected to this terminal. Now, some of you may be asking, wait a minute, but there's another thing connected over here. That doesn't matter in the parallel connection. In the parallel connection, if we're looking at two components, as long as those two are connected like this together, it's a parallel connection. There can be other nodes and things connected around them, but as long as these two are connected together, it's a parallel connection. So we can grab those two and we can reduce that as a parallel connection. So we're going to do that. Okay, we're going to grab those two and we're going to bring it over here. And how do we calculate the parallel array? The parallel of these two is going to be the reciprocal of the sum of the reciprocals. So 1 divided by 10 plus 1 divided by 10 to the minus 1 is 2 divided by 10 to the minus 1, which is 5 ohms. Okay, and that is going to be this new resistor that I'm going to call 3 plus 4. By the way, this nomenclature that I'm using, it's just a nomenclature that I'm using because I want to use it. You could actually name the resistors however you want. You could have called this one R5 or RN, or you can call them however you want. The only thing to explain the nomenclature I'm using in these problems, a series, I'm representing a series by using a plus in the nomenclature. And I'm using 2 bars to represent a parallel. Okay, just so you understand the nomenclature I'm using. Okay. Okay. And so now this combination that we have here, which is the original, the one that we have previously, which is 3 plus 4 in parallel with the resistor 2, gives us 5 ohms. Okay. Now, what could be the next step here? Can somebody tell me what we could do next?
Another series.
Correct, JC. The series would be between who and who?
Resistor 1 and the remaining one.
Perfect, correct, JC. Well done. So now we've got clearly a series connection here. And we know it's a series connection because, again, there's an uninterrupted path between these two. Okay. And from there, that's actually gonna be the last combination that we're gonna have. From there, we are going to find the, from here, we're going to find the equivalent resistance, which is going to be the 7 ohms, which is R2, plus the one that we found here from the parallel, which is 5. So the equivalent resistance is going to be 12 ohms. Okay, and that's the equivalent resistance we have for the whole circuit. So that's kind of how we reduced it. Okay, so this would be this is what they're asking us for part A. Okay, for the first, this is what they're asking us to do for part A. Okay, questions with this before we move on? Again, it's kind of it's kind of unwrapping or unpacking to identify the pairs of resistors that are in series or in parallel and find in the end one resistance that's going to be equivalent to the rest. So questions here before we do the next part. Okay, so the next part, so the last thing we did here is that from here we went to here. Now the next part is once we've found the equivalent resistance, now what I want to find is I want to find all of the voltages and currents for all of the voltages, currents, and power for all of the elements. Okay, and how do we do that? We're going to do that by going backwards. Okay, so now we're going to go from here to here to here, we're going to go backwards to find each of those elements. Okay. So let's do that. Let me just, I'm going to clear these drawings here. Just a moment. So once we've found this, the next thing that we're going to do, we're gonna start finding each of the elements we want. And so similar to the other, once we have this equivalent circuit, there's going to be a current here. That's going to be the total current for the circuit. And we can find that using Ohm's law. Okay. The total current, and that's called IT here. I called it IT. The total current is going to be equal to the total voltage, which is 24 volts, divided by the equivalent resistance, which is 12 ohms, and that gives us 2 amps. That's going to be the total current that we have in the circuit. Next up, from if we go back, that total current is going to be here. And it's actually going to be the same current that we have because it's a series connection. It's actually going to be the same current that we have for R1 and for this array here, which is 3 plus 4 parallel 2. It's going to be the same current because we are in series. These are going to be the same as this one. Okay. How do we find those currents? I'm sorry, the currents are going to be the same because it's in series. And what we need to find are the voltages in R1 and in this array over here. And how do we find the voltages? It's going to be by multiplying the resistance times the current, which is the total current that we just found. And so let's do that. Let me leave those there. So let's do that. So first off, we know that this total current, which is 2 amps, is going to be the same as I1 and the current and the 3 plus for parallel 2. And we can find the voltage in each of the elements. The voltage in resistor 3 plus 4 parallel 2 is going to be the 2 amps multiplied by the 5 ohms. That's going to be these 10 volts. And we also know that the voltage in resistor 1 is going to be equal to the 2 amps multiplied by the 7 ohms. And there now we have the 2 voltages that we're looking for. Now let's go back. We know that, so again, what we're doing is that we're going now the other way around. We're going from here to here. And now we're going to go from here to here. And so we know that this resistor, since it's in parallel, is going to have exactly the same voltage as 3, 4. So these 10 volts are going to be here. And these two are in parallel. So both of them are going to have the same voltage. And so we can calculate that voltage. It's going to be the same voltage for those two. And since we have that voltage already calculated using Ohm's law, we can find the current. How do we find the current in each of these? There's going to be a current that's going through here. There's going to be a current that's going through here, which I'm going to call I3 plus 4. And there's going to be another current going through here, which is I2. How do we find that current? We've got the voltage, which are these 10 volts, divided by the resistance for each of these elements. And so therefore, we can find both of these currents. And again, we're kind of unraveling the circuit here. I2 and I34, we have that. Now we go back. Now we go back over here. And we know that the current that's passing through I2 is going to be the current that we've got for this part of the circuit over here with R1. And so we can also do those calculations. Well, first off, we find I'm sorry, we divide, I'm sorry about that. We divide R3 and 4, we know that it's a combination of these two. So we already know the current that's going through 3, 4, which is 1 amp. And with that current, we can find the voltage in resistor 3 because it's going to be the same. It's going to be it's going to be the same current in these two. And we can also find the voltage in R4, which is going to be the 1 amp that we just found multiplied by the resistor. So we've got these two. Lastly, for R1, whoops. I'm sorry. So by this way, now we've got all of the voltages and currents for each of the components. We've got the voltages and currents for each of the components of the circuit by going back. So now, kind of as a summary, we've got the equivalent resistance, we've got the total current, current 1, voltage 1, current 2, voltage 2, current 3, voltage 3, current 3, voltage 4. The total power is going to be the power of the voltage of the power supply multiplied by the current. And we can find the power for each of the elements. And how do we find the power? The power for each of the elements is going to be directly the multiplication of these two. That's how we find the power. And so we've got 28, 10, 6, and 4, multiplying the voltages and the amps. And we notice here that if we sum all of these, we're going to get the total power. Because the power supply is providing the 48 volts, and those 48 watts, I'm sorry, those 48 watts are distributed into each of the elements. So the sum of all these has to be equivalent to the total power. Okay. Oops. Okay. It's the sum of the total power. And this gives us all of the information we need for the circuit. So we saw the example when we just have the resistors in series, we reduce, then unravel. We've got the example where we've just got resistors in parallel, same thing, we reduce, then unravel, calculate each. When we have combinations of series and parallel, it's the same procedure, but the important thing is to first be able to identify the series and parallel connections. So the first step, again, is to identify which elements are clearly in series and in parallel and start the reduction of these. Once we find the equivalent resistance, we go back, we find the total current and start to unravel backwards with regards to the series and parallel connections to find each of the voltages and currents for each of the elements. Okay. Once we have that, we can find the power for the being supplied by the EMF or the power source. We can find the individual powers for each of the elements, and these have to be congruent. These have to be equivalent. Okay. Okay. Questions with this one before we wrap up?
Professor, just
yes. Go ahead, Kevin.
Just quick question. The current.
Mm-hmm.
Where did you get the 1, 1, and 1?
Oh,
Where
the
did that
two,
come from?
the currents 2, 3, and these here.
Yeah, I know how you got the 2, but how do you get the 1?
And let me correct something here. I'm noticing that there's a, give me one moment quickly. I'm noticing that there's a mistake here. This is I4. Okay, let me go back here then. Mhm. Okay, so so we're good up to here, right? We found the total resistance, right? And then from the total resistance, we found the total current. Okay. So the 2 amps, that's clear, right?
Yes.
Okay. So from here, we're going to go back. And so if we have 2 amps going through here, and we go back, and this is a series connection, then we're also going to have 2 amps going through here. This is the same current. Okay. These are 2 amps that we just calculated. And we've also got 2 amps here. So that means that R1, the current for R1 is also going to be 2 amps. And the current for this combination here, Carmina, which is the one we had calculated, is also going to be 2 amps. Okay. So are we okay up to that point?
Yes.
Okay. So this, we already have this one. So we're already done with R1. Okay. We just calculate the voltages. We're already done with R1, okay? But now we're going to go back and calculate we're going to separate this resistor, which is R3 4 parallel 2. We're going to bring it back over here and remember that this one is a parallel combination of R2 and R3 4, okay? And so we know that in the combination, we've got 2 amps. But what is the current individually in each of the elements? Well, we know that the combined voltage here has to be 10 volts. We just calculated that. Here. The voltage for this resistor is 10 volts. And it has to be the same voltage for this one. This one also has 10 volts. Okay. And if both of these have 10 volts, using Ohm's law, we can calculate the current. And so the current is going to be the 10 volts divided by the resistor, which is 10 ohms. And R2 is also 10 ohms. So it's 10 volts divided by 10 ohms. That's where we get the 1 amp. Now, going back to what we were talking about in the previous exercise, Carmina, we've got 2 amps here. And when we go back and separate the parallel array, those 2 amps have to be distributed proportionally. And so if the 2 resistors are the same, then how is that proportionality going to be given? If they're the same and we've got 2 amps, then we're going to have 1 amp going on one side and 1 amp going to the other. Okay. If they weren't the same, then we would the values would have been different. Okay. Does that clear it up a little bit more?
Yes, thank you, Professor. I already got it. Thank you.
Good. Okay. Okay. Any additional questions with this one before we wrap up?